Hello, everyone. My name is John. I am from City University of Hong Kong. I'm a Year 1 master student and also work as a research assistant. Now, I would like to share with you about our research project, LoRaWAN-based camera with compression and image recovery algorithm. The compression and image recovery algorithm we call it CIRA. This is my presentation agenda. I will first talk about the introduction and related works of some literature surveys, then talk about some potential pain points we need to solve for doing this project, and then I will introduce the solutions, include the system design and algorithms. After that, I would like to show some performance experiments to illustrate our solutions. Finally, I will do a brief conclusion and talk about our future works. We know many IoT applications require the monitoring. For example, water monitoring, smart farming, and smart agriculture. After taking photo, we need to transmit it back to the server, but not all places have good network coverage. In some rural areas or mountainside, there are no Wi-Fi and 4G signal. To transmit the data in those areas, we need to use long-range technology, such as LPWAN, Low Power Wide Area Network. For example, LoRa, Sigfox, and NB-IoT. However, the LPWAN protocols are most in low data rate. Compared to the large image size, it is difficult to transmit image using LPWAN. In our research work, we choose the LoRaWAN as transmission protocol, as it uses ISM band and user can establish its own network. However, LoRaWAN has further regulations limitation, which limits the data uplink and downlink size, where make it become more difficult to transmit image. To conquer the pain points, we come up with our solutions, which is the LoRaWAN CIRA camera monitoring system. There are some related works using LoRa to do the agriculture monitoring. They set up a LoRa system to transmit the image data. The image is using JPEG 2000 to compress and encode. For agriculture monitoring, because the plant change frequency is very low, so the frequency of taken image is low, which can save a lot of bandwidth. They use 8-bit grayscale and set resolution to 160 times 160 pixels. Because the image is mainly taken static image, they only send the discrepancy image to further reduce the image size. Another research is also using LoRa. They use LoRa to transmit the image data. The image is encoded using different formats, JPEG and WebP, which is Google Image. They find using WebP can reduce more than 50% size than JPEG. There are many research studies about doing monitoring systems, but all of them are using LoRa. To change the spreading factors, use TDM, time division multiplexing, or other methods. No one research is using LoRaWAN to do the monitoring. This is one of the reasons we choose LoRaWAN to do the research. As a low data rate technology, send image data is a pain point. Besides, for LoRaWAN, the local governments have regulations on it. For example, in Hong Kong, it requires 1% duty cycle and need obey the TDM fair access policy. The TTN stands for the Things Network, which is a global open LoRaWAN network service provider. They provide cloud LoRaWAN service. As the organization contributes the LoRaWAN community a lot to make LoRaWAN fair use to public. They set a rule called TTN Fair Access Policy, which set an average of 30 seconds uplink times on air per 24 hours per device, at most around 36 kilobytes per day if using data rate 6 bandwidth 250 and AS923, at most 10 downlink messages per day, including the acknowledgements for confirmed uplinks. Hong Kong government also requires following the TTN policy. As you can see, 30 seconds uplink times on air is very small. Only 36 kilobyte data can be sent per day, and only 10 downlink can be sent per day. This means not every uplink can be guaranteed to receive at server, because we cannot give every packet an acknowledgement. Our idea is to use the limited resources to send image for monitoring and make image can be resent when packet lost. So we need develop an image compression and encoding algorithm and recovery protocols suitable for LoRaWAN. This is our system diagram. As you can see, we have the camera sensor node, LoRaWAN gateway, LoRaWAN server, and our data processing server, CIRA server. This shows a typical LoRaWAN network structure, which is a star topology. Many nodes can connect a gateway, and many gateways can connect to a LoRaWAN server. This is the block diagrams of the camera sensor node, CIRA node. We have the LoRaWAN module, which has the SX1262 Semtech LoRa transceiver and an ultra-low power MCU. We also have a camera module. We use ESP32 cam, which has the Wi-Fi module inside. The Wi-Fi function we will use later for the initial system setup with the operator app. The two modules are integrated to the main board, and they are connected through UART. For testing, we use 3.7 volt Li battery. Later, our outdoor version, we will change to outdoor battery. The SD card is to store the image. This is our LoRaWAN gateway. We use the Semtech SX1301 transceiver and controlled by a Raspberry Pi. Further, it will transmit the data to server. For server, we use Chirp Stack, LoRaWAN Server Stack, which is a popular open source LoRaWAN server stack. The gateway will transmit data to network server by MQTT, then forward to application server. The application server provides lots of APIs to get payload. This implementation is compatible to LoRaWAN Regulation 1.1.0. Then use CIRA server will manage the system and communicate with the CIRA node through the LoRaWAN server. Its main tasks are performing the device initialization, decode the image based on the CIRA protocol, handle the uplinks and downlink, arrange resend the lost packets, and reconstruct the image. As we mentioned, the TTN Fair Access Policy limited the size of uplink and downlink. Here, we make some arrangements of the limited resources before I explain the algorithm and protocol. In Hong Kong, we use AS923. If we take data rate 6, bandwidth 250, follow TTM policy. If we send the maximum size payload LoRaWAN packets, we can send up to 162 packets per day. Each packet payload is 222 bytes. The packet is also called as message. We reserve two messages for initialization and synchronization. Then 160 messages size is around 35 kilobytes. To equally distribute 10 downlinks to 160 uplinks messages, it is every 16 uplink will have one downlink. We define one round as 16 uplinks and one downlink. So one day we'll have 10 rounds. If each round sends one image, then the size is 3.5 kilobytes for one image. Now I will explain our CIRA JPEG encoder. First, we take a 640 x 480 pixels high-quality JPEG and store it into the SD card, then decode to RGB and scale it to 320 x 240 pixels QVGA RGB. Then we split this RGB to 3 x 4 sections. Each section has 5 x 5 MCU, which is minimum compression units. Each MCU is 16 x 16 pixels. Then we use the zigzag sequential to compress the image by JPEG decoder. This is different from the original JPEG because we know the original JPEG do not have the position information, and if packet loss occurred, the image will corrupt. We use YOV 420 and given the maximum input size 3 kilobytes to find a best image quality index. Then we use 1 byte image index to replace the 680 bytes JPEG header because the resolution and other parameters are prefixed by encoder and decoder. Finally, package it and prepare to send through the LoRaWAN. This is our CIRA protocol. First is the synchronization. It is used to synchronize the CIRA node's time to server. Because we know our CIRA node will be used in some no network coverage area, so it doesn't have the word time at initial state. To make it work as scheduled, we need the node send a synchronization uplink contains the node initial time, and then server will reply a synchronization downlink contains the time interval from real time and also some config parameters. This is the uplink packet structure to transmit CIRA JPEG because we split one image to multiple packets in one round. We need less server know the number of packets per round and the image index and the packet index, which shows in yellow part. For green part, which is the CIRA JPEG. To let CIRA node know which uplinks lost and resent, we need send the loss information by downlinks. We define the downlink structure like this. The first byte is telling how many uplinks need to be resent, and if support regional and discrepancy. Then followed by the blue part. It shows the lost uplinks image index and packet index, and we define the priority. For priority, because by the TTM policy, between uplinks need fulfill certain intervals. In our case, is 8.9 minutes. So we need to wait around 2.5 hours to get a downlink. However, user may want to send the downlink immediately instead of wait until 2.5 hours. After that, if we enable region, we need tell the node the rectangular position information for the region, which shows in the green part. If we enable the region and the discrepancy, we can reduce the transmission data size. This is our CIRA system protocol flow diagram. We illustrate the protocol between camera module to LoRa module, CIRA node to server, and the recovery protocol. As mentioned, we reserve 16 uplinks per round, so we take 2 uplinks for resending the previous lost packets. Our system has a setup mode. It uses for initial setup and fetch the high-quality photo. As mentioned, our node supports Wi-Fi function. User through the operator app can set up it and get the initial image. Initial image is important because user need wait 2.5 hours to get a photo. But if the packet lost, user need wait more time to see it. Before receiving the lost packets, the lost part is shown black. Then we use 2 previous images to cover the lost part. An initial image is for the initial condition, so that we can improve the user friendly. Another is we store the 640 x 480 high quality image to SD card. User can collect these photos from SD card through Wi-Fi when they want. Work mode will follow the CIRA protocol. This is a simulation result. We divide to 4 phases to do the comparison. You can see in the table, we use JPEG, JPEG without header, CIRA JPEG, and the CIRA JPEG with recovery. The right-hand side shows one round sent 16 packets for an image and lost 2 packets. If only use normal JPEG, it is easily corrupted. If we remove the header, the image also corrupts, but the quality is higher. If using CIRA JPEG, we can limit the damage part within certain area and the quality still remain high. And then use recovery algorithm. The lost parts can be reconstructed, but quality reduced a little. In a conclusion, we design and implement the CIRA system using CIRA algorithm and protocol is suitable for LoRaWAN monitoring system. For future works, we will support more encoding methods. Our group is also doing another project related to LoRaWAN called Secure RISC-V IoT chips. We designed our hardware architecture based on RISC-V to make LoRaWAN application more secure. This is the end of my presentation. Thank you for listening.